go.
All righty, so when you go to your calculator and you type in there, you go, you got your screen here and you type in 0.1 and then you go hit the e to the x button, and essentially when you're computing this and it gives you some number out. The way it does that, what your calculator is doing, what any computer is doing, when it cranks this out, is it understands a secret formula for E. It knows how to do this. And in fact, it knows that if I put something here, and I take 1 plus that thing squared over 2, plus that thing cubed over 3 factorial, so that's 6, these are factorials here. And if I keep on doing that, I will get the true value. If I could do that forever, I would get the true value. Your calculator says, I'm going to keep doing this until the digits stop changing for maybe like the first 10 digits or something like that, and then just stop. This thing here is called a power series. And this is our ultimate goal for the rest of the semester, to get to a place where if I gave you something like this, x times sine of 3x, you could literally just write it as a polynomial, an infinite polynomial that goes on forever. That's the goal. That's where we're headed. And once we get there, things are going to be good. Was that me making that ding? Or no? Okay, cool. Just as long as it's not like coming from my head and inside my head and projecting outward into the room, everything's going to be good. So last time we talked about, or last couple of times, let's just say last week, we talked about geometric series. This is a very specific type of series that looks like this. So we got some n starts at some start, and it goes to infinity, and we've got some constant times a number that is being raised to higher and higher powers. We have that common ratio, right? So this was our common ratio. That's really the only series we know how to do anything with, but we completely understand that series. I know that if this common ratio is less than 1 in magnitude, so if r is less than 1, then I can add this up. It's just going to be the first term, whatever that turns out to be, over 1 minus r. We own that series. There's many other series we know nothing about, but we're going to learn a lot about in the next couple of days. So for example, let's take a look at a very simple series. This is called the harmonic series. It's actually one of the most important series we'll talk about. Hello. Howdy. So the harmonic series looks like this. And I want to talk about how this is completely different than anything we've seen so far, but it just keeps on going like that. Anybody play instruments? Yeah. Why do you think that's called the harmonic series?
Well, it just keeps going up.
Keeps going up. Yeah. What are these ratios? Like if you had like string
They're
instruments.
all certain step apart from each other. Like half to a third would be.
Oh, think
They're like intervals.
They're intervals. Yeah. So they're definitely intervals. So like if you have I know about guitars. If I have a guitar and here's the neck, there's like a little bar here that the strings come over, right? You got the keys up here, and you got strings wrapped around. You got the string that comes all the way down. There's like a sound hole here, and then there's another bridge down here, and the string comes across that. If you just pluck that string, just pluck it like this, you get all sorts of vibrations in there. And all those different frequencies make up the tone of that note. You can break down this frequency a little bit more. If I place my finger at exactly the halfway mark, so I just lightly touch there, and then I pluck here, I will hear a very beautiful tone, like a bell ringing. Anybody ever heard these? Like harmonic, they're called harmonics.
Violins have them too.
Violins have them too. I imagine any string instrument would have this.
Because they have them like a quarter of the way, a half of the way, and...
That's it.
Okay.
Exactly, so that's where I'm getting at with this. Exactly, so if I lightly touch here, it breaks the string into perfect halves, and when it resonates, it creates a node here that stays fixed, so the resonations kind of just look like this, and there's always this fixed point in the middle. That sounds really beautiful. If I do that at a third, so if I do it down here at the third mark, or even at the 2/3 mark down here, I get a completely different tone. And if I do that at a quarter and a fifth, and it starts to get really difficult to do this and have it be heard when you start getting down into like the 6th and 7th and 8th, and it's really hard to find those exact positions. But these are called harmonics on a guitar string or on a stringed instrument. And sometimes you'll hear like someone who's really good, like you ever heard some great finger tapper, and they'll like be tapping, all of a sudden you hear like that bell sound, that beautiful like pure sound. That's because they're hitting a harmonic and then tapping on the string, or tapping at a harmonic. So anyway, this idea of these harmonic ratios has been around for a long time. This got the name harmonic series. If I keep adding these up, it seems like the pile is getting, is getting bigger but slowing down. So like, let's just say this is 1 unit high. And then I take another block and put that up here, and that block is half a unit high. Then I've got a block that's a third of a unit, third of that high, and I put it here. And then a fourth, and if I just keep adding blocks of those different heights, it seems like it's starting to slow down and that this might reach some top. Turns out it doesn't. It turns out that that series keeps building up and building up and building up and never accumulates to a finite value. You want it to get to 1,000? You just add enough terms and you'll get to 1,000. You want 10,000? Keep on going, you'll get there. So that series never settles down like we've been talking about with sequences. Here, though, if I take this series and I tweak it just a little bit, if I do this, so right now there's nothing that you need to like record. I'm just like talking through where we're going. If I do that, this series does add up to something very finite that we can actually compute. We'll be able to compute what is that sum. If I take this sum, so it's a lot like the harmonic series, but I'm squaring the bottoms. That series will add up to something. This seems like it's kind of the same thing, right? What do we got here? So you got a block of unit height. You're going to add a thing of a quarter to it, and then I'm going to add a 1/9 to it, and then a 16th and so forth. Turns out this actually piles up to a finite level. Eventually it just stops growing. And in fact, we won't be able to show this in here, but you could add this all up and it adds up to pi²/6, which is a weird fact. This one here adds up to, and we'll be able to see this, the natural log of 2, which is quite weird as well. So like you're looking at that and you're like, I don't know why that's true. I guess I'll believe it. But soon you'll be able to actually understand why that's so. But the heart of where we're going is that you can understand these things called power series. Essentially what we're going to do is learn to take a function and break it into a spectrum. So we're thinking about this mathematical prism where we pass this through. We've got this little prism down here, and it breaks it into its fundamental parts. And you can get a deeper understanding of the function by doing this. So that's where we're headed. But we've got a little bit of terminology and work to do first. So let's just talk about general series. And then we'll get into the specifics. So for general series, first off, let's just look at some notation and refresh our memory on it. So if I write this out, this is a sum. The first index is n sub 0, so this is a sub n sub 0 plus a sub n sub 0 plus 1, on down, and keeps on cruising. That's an infinite sum. These are called the terms. This n is called the index. This is the starting index. And for us, this is always going to be our final index. We're always just going to assume things keep on going forever, so it never ends. The sum never ends. So how do we make meaning out of this? How do we get a hold of something that's infinite? Well, what we do is we turn it into something that's finite first and study that. So to understand this series, we turn it into, first, a finite series. To understand an infinite series, we study its partial sums. And we saw a little bit of this last week, but we're going to get a little more serious about it today. So the partial sums, we call it S sub n, and it's equal to the sum of the first n terms. In the series. So up there, I would just grab the first n things that I had. Let's say I've got the series, suppose we had just this series here. It starts at 1, goes to infinity. Then S sub n is a1 plus a2 plus all the way up to the nth term. So again, there's just n terms here. So now we're going to play a game. We're going to actually gain something super deep from this in just a minute. But why are we doing this? Because this turns the study of this infinite thing into a study of a sequence of things. So we get a sequence, which is just a list of partial sums. Let's write that out. The first one, S sub 1 is just the first term. S sub 2 is a1 plus a2. See how this is going? S sub 3 is some of the first three things. Whoop, wow, easy. And then all the way down to S sub n. And then that keeps on going forever and ever and ever. But notice that this is a sequence. It's just a sequence of numbers. And here's the game. We're going to say if that sequence of numbers, if that list of numbers settles down to something, then the sum is equal to that value. So here's like one of our most important things here. If the sequence of partial sums converges to some number s, so remember what that means. It may be oscillating, but it still settles down. We want this picture. We've got our partial sums settling down onto something. So like this. Call that S right there. Settling in on it. Lots of ways to settle in on that. I just drew one. Then we say this series converges to S, to the thing that that sequence goes to. Otherwise, the series diverges. We have converges and diverges. One of the biggest questions we're going to have in this class is, I give you an infinite sum and ask you, does it converge or diverge? And that's where things are going to get interesting. We're going to have a lot of different ways to approach it, a lot of different tests to use along the way. So when I say interesting, that's generally challenging. But we're going to take it bit by bit, and I'm going to be there with you, so we got it. A really cool thing that comes out of this. Let's suppose that I have a series that converges. Well, that means that its sequence of partial sums converges to a number. Then S sub n, which is a1 plus a sub, all the way up to a sub n, converges also. Let's say this converges to S. Then the sequence converges to S. What does this sequence converge to? So here's a slightly deeper question. I just want you to think about it for a minute. Here's this sequence right here. So S sub 1 just goes, this is just S sub 1, S sub 2, S sub 3, down the way. What does it mean to write this? What do we think? Let's talk about it. If I write this, how does that differ from this? Well, let me ask a different question. We know that S sub n converges to S. What does S sub n minus 1 converge to? What do you think? Let's take some guesses. Yeah.
Would it be S minus n?
Ooh, I like that. So you're saying over here S minus n. So let's just keep in mind this n is something that gets worked out by the limit.
Right.
Yeah, so the n wouldn't show up over here because we're letting n go to infinity.
Right.
Right? What if I told you this? Does that make sense? This is just the same sequence. This one's just knocked back one level. So in other words, think about it like this. Here's the picture. If we've got, say here's S, and here's S sub n. Here's S1, here's S2, S3, S4, S5, 6, 7. So this thing right here, this is just that thing is headed toward S. This thing is headed there. It's just like one slower. This is essentially the same sequence. It's just missing some starting terms. That's about it. So I just want you to and I'm happy to talk about this if that doesn't make sense. These are essentially, let me write this out, the same sequence as n gets large. This one's just missing one thing in front of this. So like if I call this S sub 1 or S sub n, shit. Oh, I got it. Here's a good, okay, I got this. I'm trying to think of a way to explain this for you, but now I think I do have it completely. So here's n, and here's S sub n, and then here will be S sub n minus 1. So let's just say n is 2, and S sub n, S sub 2 is 1. I'm sorry, this isn't exactly clear here. Not a good, let's make a different chart. Apologies. So, let's say S sub 1, oh, okay, how about this? S sub 1 equals 1. S sub 2 equals a half. S sub 3 equals
equals, let's see, a quarter, and then S sub 4 equals an eighth. And that thing seems like it's headed down. So this is maybe this is the sequence S sub n. Well, no, I'm not really saying that. This is S sub n. S sub n minus 1 is basically the same sequence, you're just picking it up at a later point. So this has all the same elements. They're just out of sync by one step. I think that's what I want to say. Just out of sync by one step. So let me draw that right over here. So this sequence would look like this. S sub n minus 1, S sub 0 doesn't really exist. God damn, this isn't making any sense. Boy, I'm sorry. I don't think this is making any sense.
Are you just trying to say that it's like it's shifted over by?
Yes, that's what I'm trying to say, and I'm trying to like make it too detailed, I think.
Well, on that graph, then could you just like
Just pick it up.
everything's just back one?
Yes, that's what I mean to say.
So it's the same graph.
Okay, thanks. Yeah, exactly. Yeah,
Okay.
yeah. Thanks. There you go.
Yep.
There you go. That's it. It's the same damn list of numbers. We're just like picking it up one space a little bit to the left. That's it. Okay. I like what Sophie said here. It's just the same list. So the same limit. It's just missing the last term. So let's actually write out what these are. So S sub n is this. Oh, here's what I should have done. S sub n minus 1 is this. There we go. Oh, just that. See, it's this got that right term, and if I put that there, then they totally sync up. S sub n is this, S sub n minus 1 is this. You can see that S sub n minus 1 will be there on its next step, I think. What happens when I subtract these two things? What do I get when I take S sub n minus S sub n minus 1? What's the difference between those two? A sub n. Yeah, so all this stuff cancels, and that's equal to A sub n. Let's put that up here because this is actually going to give us something. But boy, I'm feeling sweaty. I was feeling like really desperate there. It just, the words weren't coming, so Sophie, thanks. Appreciate your presence.
Yep.
So, cool, thanks. So we got this, we got A sub n. Where does this go as n goes to infinity? Well, it goes to S. Where does this go as n goes to infinity? It goes to S as well. So where does that mean A sub n goes as n goes to infinity? 0. 0, exactly. So this goes to 0. Okay, so now why are we saying this? Because this is actually one of our first tests. We have to tweak it just a little bit. But let me summarize. So, if a series converges, so let's say our series looks like this, sum A sub n, then its terms must die out. They must go to 0. Its terms must die out, i.e., let's summarize this here. If this thing converges, I'm going to show you a nice little bit of notation. So to write this means it converges. Just say it's less than infinity. That implies that the terms go to 0. Any series that adds up to a finite thing, the things you're adding up have to shrink to 0. If they don't shrink, then you're just kind of adding things with thickness forever and ever and ever. You've got to have the pile, the things you're piling, get smaller and smaller. So let's think about what this is now, because this is not super useful. All this says is that if I know the series converges, its terms die out. But what we want is something that helps us understand if the series converges or diverges. So, first off, we're going to talk about the contrapositive of a logical statement. The contrapositive of if P, then Q. So that's a logical statement. It's called a conditional. If the light switch is on, then the lights come on. So the contrapositive of that is the statement. If not Q, then not P. So you flip who's implying who, and you negate both. So let's think about that. If the switch is on, if the switch is on, the lights are on. If the lights aren't on, the switch is not on. Yeah, so that works. So it's like, it's weird that it's true, but this statement is exactly the same as this logically. You could make a truth table if we wanted to do that and see that they were exactly the same logically. So what is the contrapositive of this? What's the contrapositive of that statement? So this is if, then. Yeah, Sophie.
If it's not 0, then it diverges.
There we go. If the terms, if the sequence, the things you're adding up don't converge to 0 themselves, the sum diverges. So for us, so here, we get a new test. This is called the nth term test, but let's write it up here. Here we get, if a sub n does not converge to 0, then the sum of those a sub n's diverges. This is called the nth term test, sometimes called the divergence test, because it's only good for determining divergence. So let me ask you a question. Does this series converge? We'll start at 4 so that that thing doesn't go to 0. Does this converge? So we look at that, and the game is going to be like this from now on. I'm going to give you a series, and you're going to go, do I recognize the series? And right now, we only recognize one series, geometric. How do I know this isn't geometric? How do I know this isn't a geometric series? What does a geometric series look like? Yeah, something to the end, right? So same like if you started writing this out, and some remember write this out. So the first term n equals 4, and I know you have a question, Sophie, so I'll get to that in just a second.
You're good.
Number 1 plus when n equals 5, we've got 11 over 2 plus, and then we're just adding by 2 each time, I guess, on top over 3. Is that geometric? I mean, to get from here to here, you multiply by some god-awful factor. It's not the same god-awful factors from here to here. Not geometric, but I could tell that right off the bat because there's no exponent n up here. So just make a note that there's no something to the n in the series, so it's not geometric. We're going to practice this every time we get a new series. So it's not geometric. You've got to have the index as an exponent, and that's what Sophie was saying at the beginning. Yes, ma'am, and you had another question. Do you remember it? It's been a long time.
Do you need to use L'Hopital's rule for that then?
We will. Yes, in just a second. Yes, we will. So it's not geometric. Can't do that. I wish it was. Life is easy when it's geometric. We can even add it all up.
So then I think, okay, well, what other series do I know? I don't know anything else at this point,
But I have that test over there. So I look at this and I say to myself, is this dying out? Man, I hope it doesn't, because then I'm done. So we look at A sub n. So not geometric, let's consider the divergence test. We don't know. So I write out the nth term, and then I take the limit of that as n goes to infinity. And here's where we do need L'Hopital's rule, Sophie. Yeah. What is the limit? Scotty, what's the limit on that? 2. You got it. Solid. Limit is 2. Is everybody good with that? 2 over 1? Yeah. Not 0. Therefore, this series diverges. So since A sub n does not die out, the series diverges. I don't have to do anything else. It will never add up to something finite. I'll give you another one. Does this series diverge? Got a pretty solid answer there. Seeing like lots of good solid answers. What's the nth term? What's A sub n?
0.
Oh, well, hold on, the limit is, right?
Yeah.
Yeah, so A sub n is this. That converges to 0 as n goes to infinity. That doesn't tell me anything. So the only time we know, this does not mean the series converges. You've got to be really careful with this conditional. So this tells us nothing. And I would make yourself a little note. Note, A sub n converging to 0 does not mean you have convergence. The only thing that works is if it doesn't, we only know A sub n not going to 0 implies divergence. Because it's going to turn out this series diverges. This harmonic sum does not add up to something finite. We'll prove that a little bit later. But that series diverges. Good little thing to note right up front. Let's see here. I've got a copy of my current web work here. I want to make sure to hit everything. And that's a lot of that. Yeah. Oh, good. Okay, cool. Good. Let's push this a little further. Oh shit, let's just get one whole grade class of things in, and I'll just prove it to you next time. So I'm just gonna give you a whole class of series, because I just want to get working with them, and the next assignment will be more important for proving this, but useful fact. I have a sum, n equals, and you can start anywhere you want, goes to infinity. I've got 1 over n to the pth power. This series converges if p is bigger than 1, and it diverges otherwise. This is called a p-series. And it's kind of the flip side of the geometric series. Notice here, in the geometric series, the n is the exponent, but here the n is the base, and the exponent is fixed. So it's really the perfect companion for the geometric. So let's make those little notes. Note, exponent is fixed. It's the base that moves. Complete flip of a geometric series. So, what if I gave you this series? series converge or diverge?
Converge.
What's N?
Or
Or what's P? Sorry.
P is 1/2.
P is 1/2, so we diverge, right? Yep. Because it's only when that exponent is bigger than 1. So here, P equals 1/2, and that means divergence. And I'll prove this like first thing on Friday, but let's just have fun today. So now you can see that's just a P series. The harmonic series is just a P series. In fact, it's like the borderline, right? Because right here in the middle, this is P less than or equal to 1. This is when things get bad, right at P equals 1. So that series diverges, but look at this. If I did this, put a lot of zeros and then a little 1. Converge or diverge? Converges, because the exponent's bigger than 1. Even though it's going to go slow, it's going to add up to a big number. We'll get some Excel experiments in here. I wish I could actually easily access Excel for us over there. So what's up with this? We've got this. Now you know another series. You know a whole bunch of them. You also have your geometrics, right? So these are known things. These are things we own completely. This and P series. Completely own those. What though if I get something like this? What if I get a series that looks something like this? 7 over n to the 4th n equals 1 to infinity. Okay, so now that series doesn't look exactly like that, because these have 1s on top, that's got a 7 on top. But I can just bring that 7 out in front and rewrite it like this. And now I see this is a convergent P series, so this whole thing converges. That's not too bad. In fact, let's just write up a nice little property. If these two series converge, then so does, or so do, any multiple of that series. So here I just multiplied everything by k. You can just pull that k out in front. So that converges, and also, if I take the sum or the difference of those two series. So, let's check out the second one. We used the first one just right above. The second one, about this? Got sum of 3 over n squared minus 2 over n to the 5th. N equals 1 to infinity. What kind of series are you seeing in there? What do you think, Cam?
That looks like kind of how you've got it written. It's two different series being subtracted from each other.
Yeah, with multiples on top, right? So yeah, exactly. And they're both P series. They're both convergent P series. So I expect this to converge. Yes,
Can you do 2 steps at once and pull the 3 out in front and separate it?
I would do that, absolutely. So I just pull everything, just rewrite it right away. So it's 3 sum 1 over n squared minus 2 sum 1 over n to the 5th. This is P equals 2 greater than 1, so it converges. This is P equals 5 greater than 1, so it converges. So the whole dang thing converges. So I break things down into the building blocks that I understand. Cam, yes?
If we've got something similar to that, but instead of like n to the power of 5, we had like n to 1/2, for example, does that mean the whole thing diverges?
That is, that's good. Yeah, absolutely. So let's check it out. That's, you're reading my mind. That's where we're going next. Good work. So, Cam is suggesting this example. Let's take a look at it. We've got sum of, like, say 3 over n minus 2 over n to the 4th, something like this. So Ken was suggesting, what if we had like, and you used like to the 1/4. Let's go with I like your example. And then they're nice reciprocals of each other. That's pretty. So this is 3 sum 1 over n to the 1/4 minus 2 sum 1 over n to the 4th, and this diverges. So p equals 1/4, less than 1, so it's divergent. And this one converges. But they both have to converge as you hypothesized. So this whole thing diverges. Good stuff. Yeah, nice. One last thing I want to show you. Let's see, let me grab one of these, like, let me grab a problem off of the web work here. Well, actually, let's make a general statement first. So I got one more property, and then we'll do some work together. Comparison test. This is called the direct comparison test, DCT. So if this series converges, and its terms are all positive, let's just say they're all positive, and B sub n is a sequence that is bounded above by A sub n for n greater than or equal to some starting point, then this series converges. And think about what this is saying. It's really just saying that that series is on top of this one. So if I have a series that converges, and everything's all fine, and I'm adding it up, and shit, if I start drawing pictures, trouble will happen. But if I have a series that's underneath one, and let's see here, B sub n is greater than 0, 2. If that series bounds this series and that one converges, then this one converges too. And then also, if A sub n diverges, so if this thing is blowing up and I have something on top of it, that thing also blows up. So if A sub n diverges, let's say everything's positive, and B sub n is greater than or equal to A sub n for n past some point, then the other series diverges. So I think I can draw kind of a picture here. So if I have a convergent series, then all series that live underneath it are convergent. If I have a divergent series, then all series that live above it are divergent. That's not a bad picture. It kind of makes some sense, I think. Never drawn that picture before, but I kind of like it. Not bad. So one last problem. It's unlike your web work. Let's actually do it together. I printed out my own copy for myself here. Oh shit. Yeah, I got one last thing. We'll finish this up and then we'll talk about one last little thing that's pretty fun, actually. So here's there's a couple problems on the web work that are something like this. Let me give you one. For all n, oh my god, that thing is fried. Come on, baby, there you go. For all n, that's pretty bad, but it works. For all n greater than 1, n over 5 minus n cubed is less than 1 over n squared. True or false, this series converges. What do we think? So we have to piece together some things here. Oh, that's right. Yeah, well, how come, Scotty? That's right.
Because the denominator, in this case, it's growing in the negative direction, but it's growing to infinity much faster than the numerator.
Yeah, we got to be careful with that though, because this does that same thing too, right?
Mm-hmm.
Like here, the bottom's going up, and this doesn't converge.
Mm-hmm.
So think in terms of what I was just like these comparisons here, right? So here I'm saying that the terms of this thing are less than or equal to these numbers. What does this series look like?
That's
That does converge, right? So this series, how does this series relate to this one in terms of like the value? Less or more, equal? Each of these terms is less than each of these. So what is the sum in relation to this? How do these two relate to each other?
less than.
Gonna be less than, yeah, right? Like if the things I'm adding up are less than all the other things, then the sum is gonna be less. So this one is strictly less than because of that. We know this series converges because this is a convergent P series. So this series converges as well. I'm giving you even less than they give you. They literally tell you that this converges in the homework because they hadn't talked about that
And
yet.
that's only because of that first thing where it's greater than 1.
Yes, yes, absolutely. Let's do one more. Okay. No, I think honestly, I think I'm just gonna cut you loose on those. I think you got it. It's just, we'll talk about it if you don't. I just want to show you one more thing. But that's, there's like 1 or 2 problems where it's just using this result right here. One last thing to show you. Here's a series we can add up. It's a very special kind of series. It's a really cool kind of series. It's called a telescoping series. Here's a special series. And what's cool about this special series is we can determine if it converges or diverges, and we can also add it up. We can actually add these up. So these are called telescoping series. I'm afraid I need a better pen because that is not going to show up. But I don't have a better pen. I lost all my cool black pens. Oh, here, there's something. Come on, please, baby. Oh, God. Give me a blue. Give me a dark blue. Yes. Okay. All right. Telescoping series. Let me give you an example. Let's say I had 1 over 3 times 4 plus 1 over 4 times 5, 1 over 5 times 6, 1 over 6 times 7, on down the way. So, does this converge? Let's answer that question first. So what I need to do is step 1, get this into series notation. So let's get it into series notation. I'm going to get you started, but I'd like you to try this because this is actually also part of your web work, writing things in series notation. Could you give that a shot? You get to pick the starting index, ending index, and the form of the sum. Yeah, looks good. Yeah, absolutely. Yeah, yeah. I would just put parentheses, but I know what you mean. You do. Yeah, yeah. Where's your index start at, Cam?
For the first one, it started at 3.
Start at 3. That seems like a fine place to start. Everybody feeling good on this? Let's see. So the first term is 1 over 3 times 4. If I start at 3, then there's the 3, and there's the 4. And then when n equals 4, that's 4 times 5, and next 5 times 6, and those all get added together. Did anybody do something different? Because there's actually infinitely many ways to do this. Yeah, Dan?
I was thinking n factorial over n plus 3 factorial.
Oh, hold on. So like this?
Yeah.
Huh, and plus, I like this, like that. Yeah, yeah.
Oh yeah.
Oh, yeah. That's pretty freaking fancy, my friend. But that works, yeah, goddamn, that's right. That's a good job. That's too fancy for us, but that's good. Did anybody start the index at anything other than 3? What'd you do, Scotty?
Started at 1 and then went n plus 2 times n plus 3.
I like it. Yep, that's also totally viable. You can start anywhere you want. You just gotta adjust, right? So I literally could, this is the same as this, as the same as I could start at 17 for some weird reason, if I really wanted to. As long as I get 3 times 4, so here I would take n minus 14. Wait, is it 14 or?
Yeah.
Yeah, and then n minus, I hear it like Cam's whispering, so. and then this 13, right? Yeah, there we go. So that's another way. There's literally infinitely many ways to do this. These are all the same. It doesn't matter. That's good news. Watch this. Let's go with this one here. This is kind of like the lowest energy one, so I like it. What if I write it like this? Sum of, now this, we've done something like this before. Do you remember partial fractions? Yes, yes, yes. This is actually writable as 2 fractions added together. And I could do a partial fractions expansion on that, but I'm gonna save us all a little bit of misery and just show you and see if you believe me that when I combine those 2 fractions, I get that fraction, right? Because this one I'm gonna multiply by n plus 1 over n plus 1, and then this one I'm gonna multiply by n over n.
Why is it negative?
Here, let me show you. So, to get them together, I gotta get common denominator, right?
Mm-hmm.
And so I'm gonna multiply this one by n plus 1 over n plus 1, and I'm gonna multiply this one by n over n. And notice how the n's cancel and just get me that. Yeah, sound good? So we can do that here, and let's write out the partial sums. So let's see, we're starting at 3 to 4. So let's start at least writing this thing out. What the heck is going on here? So when n equals 3, I've got 1/3 minus 1/4. I don't know why we got that there. And then when n is 4, I've got 1/4 minus 1/5. Notice that if you add these together, you get 1 over 3 times 4. And if you add these together, you get 1 over 4 times 5. So we're getting the sum that we had. Are you seeing anything interesting? getting a lot of cancellation. Notice that the inside terms are the same, they're just opposite sign. That's why this is called a telescoping series, because it kind of folds back up. The way to get at it is to write out its nth partial sum. So to find the sum, compute S sub n. So the nth partial sum, let's see. Here is S sub 1. Here is S sub 2. Here is S sub 3. So let's see if we can be slick about this. And maybe let's just write it out down here to help ourselves out. So S sub 1 is going to be 1/3 minus 1/4. S sub 2 is going to be, what's S sub 2 simplified to?
So 4/20ths.
Is it that time of year yet? Wait, what?
9?
That's what, no, so, okay, I think, you're getting all like more mathy than I'm even getting, so let's go, like, just the fourth cancel, right?
Oh.
So 1/3 minus 1/5, does that make sense?
Oh, okay.
I think you're thinking, I'm thinking for something much deeper than I'm looking. Does that make sense?
Mm-hmm.
And then what's S sub 3? 1/3
Minus a 6.
minus 1/6. Are we starting to see a pattern here? What's S sub 4? Minus a 7. Cool. What is S sub n? Can we generalize?
Is it like 1/3?
1/3 minus
1/n.
close.
Plus 1.
Plus, so how do you move from that index to that?
Plus 3.
There you go. So S sub n, we can write like this, because all the stuff canceled. What is the limit on that as n goes to infinity? Let's write it up over here. So S sub n is 1/3 minus 1/n plus 3. Where does that go as n goes to infinity? 1/3, because this dies, right? Goes to 1/3, and that's the sum. So this collection of numbers here, this crazy sum, broke it down, expanded it out, it collapses, and makes life easy. And somehow it comes to 1/3, which I find actually pretty shocking. Cam is about ready to like fall out of his chair. Which makes me happy. All right, my friends. We now have what we need to do the web work. And we could start working on it right now if you want. Maybe let's just take a look at it together, like just take like 10 minutes. Just look at it together. And then Friday we'll work on it together some more. I might have a few things to say, but we'll get a lot of work done on Friday. I think I got this due on Sunday night. So. Hourly restroom break. Be right back.
Anybody got stuck or anything at this point?